Up to the last lecture, we have covered the electrostatic portion of the electromagnetic field theory. Now, from this lecture onwards, we are going to study the magnetostatic fields. So, let us start the first lecture of the magnetostatics. So, as we have seen in the case of electrostatic, here also we will see there are two major laws that governs the magnetostatic fields, and these laws are Biot-Savart's law and the Ampere's circuit law. In the case of electrostatics, we have seen the Coulomb's law is the general law of electrostatic. Here the Biot-Savart's law is the general law of magnetostatics. And also we have seen the Gauss law, which is the special case of the Coulomb's law. Here the Ampere's circuit law is the special case of the Biot-Savart's law, and it is or it can be easily applied in problems involving symmetrical current distributions. So let us first understand the Biot-Savart's law. According to the Biot-Savart's law, it states that the differential magnetic field intensity dH produced at a point P by the differential current element IDL is proportional to the product of ideal and sine of the angle alpha between the current element and the line joining the point P to the element, that is the current element, and is inversely proportional to the square of the distance r between P and the current element. So this is the statement of the Biot-Savart's law. Now mathematically this Biot-Savart's law can be represented by this expression 20.1, that is the differential magnetic field dH is proportional to ideal into sine alpha by r square. Now we know that this expression 20.1 can be represented as dH equals to k into ideal sine alpha by r square, where k is the proportionality constant that we know, and in SI unit k equals to 1 by 4 pi. Now if we put the value of k in the expression 20, we will get dH equals to ideal sine alpha by 4 pi r square. Now this expression 20.3 can be represented in vector form. Because we are studying the electromagnetic field theory, so all the expressions must be represented in vector form. So how to represent this expression 3 in vector form? Let us see that one. So from the definition of the cross product, it can be easily noticed from that this equation can be represented in vector form. So if we write this expression in vector form, so you see that here sine alpha is present, so we can write dh here is the vector equals to di. Di is the current element in this dl length cross air is the unit vector from this point to the point towards the point of our observation, that is the unit vector air by 4 pi r square. So we know air by r square equals to r by r cube, so this expression can be written as idi cross r by 4 pi r cube. So this expression 20.4 is the vector representation of the Biot-Savart's law, where you can see that this r is the magnitude of the vector r, so the mod of vector r, and air is the vector r divided by the magnitude of r. And di, here di is the small current in the conductor length dl. So current element di is the current element in the conductor length dl. Now this direction of dh can be determined using the right hand rule, which we know with the right hand thumb pointing in the direction of current and the right hand fingers, the other fingers, encircling the wire in the direction of dH. So if the current is flowing in this direction, so the magnetic field direction will be in this direction, because the right hand thumb will be directed along the line in which the current is flowing. So other fingers encircling this current flowing through the wire will be the direction of the magnetic field DH. So that we can see here, you can see that according to it from this diagram, that if the current is flowing in this direction, so this thumb is showing the direction of current, and the other fingers encircling the current carrying conductor will give us the direction of the magnetic field DH. So here the direction is given. In another way also we can represent, or we can see the direction of the magnetic field. So this is called the right hand screw rule. So to determine the direction of DH, we can use the right hand screw rule. So according to this rule, with the screw placed along the wire, so this screw is placed along the wire, suppose the wire is presented in this direction and current is flowing downwards and pointed in the direction of the current flow. So here the screw is pointed in the direction of the current flow. So now the direction of advancement of the screw. So if we rotate the screw in this direction, so screw will be advanced in this direction. So that is why the direction of advancement of the screw is the direction of DH, that is magnetic field intensity. So magnetic field intensity will be directed along this, which is given in this diagram. Now, for the sake of our simplicity, for simple understanding of the direction of the magnetic field intensity H or the current I, we will use a small circle with a dot. Here you see that the small circle with a dot, or cross sign, depending on whether H or I is out of or into the page. Now if we consider this circle with a dot, that means we will consider H. If we consider the direction of H, so the H is the magnetic field which will come out of the page, because you know that in 2D diagram it is difficult to represent 3D picture. So that is why we are going to consider that, say, current is flowing in this direction. So the current and the current carrying conductor can be drawn in 2D diagram or 2D page. So now if we draw the current carrying conductor and the current direction, then this will represent the current, the magnetic field is coming out, and this represents that is the circle with cross will represents the magnetic field will, it is moving into the page. And if we consider the current, again the same way, the I is coming out and I is going into the page. Now this is all about the Biot-Savart's law. So according to the Biot-Savart's law, we can find out the magnetic field intensity, as well as we can understand that in which direction the magnetic field is moving. That means the direction of the magnetic field. Now, just like the different charge distributions, like the line charge, the surface charge, and the volume charge in electrostatic we have seen, here we have the current distributions, like the line current, the surface current, and the volume current. So here these three pictures is showing the line current, surface current, and volume current. Now if we define the current density or the surface current density K, then, and which is in ampere per meter, and if we define this is the K, if we define the K is the current density, surface current density, so the current element present in this area can be represented by KdS. Similarly, if we consider the current density, line current density is I here, then the current element present in this dl length will be IdL. Similarly, if we consider J is the volume current density in ampere per meter square, the source element, that means the current element present in this volume dV will be JdV. So here in three cases we are considering the element of current, that means the amount of charge which is moving. So here the amount of charge present in this dl length which is moving, so that is equivalent to the amount of charge, that is kds, which is moving in the surface, and also jdv, that is the amount of charge moving through the volume. So that is why equation 20.5 is representing the line charge or line current, surface current, and the volume current as are equivalent. Now I repeat why it is equivalent, because we are considering the current is moving, that means the charge is moving. Charge is moving means the current. So the current element, the charge enclosed in this line dl, or in this length dl, is the ideal. So this amount of charge is moving, for that we are getting the magnetic field. Similarly, for the surface current, this is the area ds, and the current density is k ampere per meter. So this amount of charge is moving, so we will get the amount of charge is moving means the current, surface current we will get. Similarly, we will get the volume current. So all these cases, for all the three cases, the amount of charge moving, that means the current. So that is why idi equivalent to kds equivalent to jdv. Now we have seen in the case of Biot-Savart's law, that is the magnetic field intensity dH, which is equals to idi cross r by 4 pi r cube, or idi cross air by 4 pi r square. So in terms of the line current, in terms of the volume current and the surface current, we can write the magnetic field intensity. So here we have seen the dH. Here you can see that the dH equals to this expression. So if we take only the h, then h will be the h. So we need to take the integration. So if we take the integration, it will be h, and then for the line integral, it will be line integral. For the surface current, it will be the surface integral. For the volume current, it will be the volume integral. So here for the line current, h will be equals to the line integral of idi cross air by 4 pi r square. Similarly, for the surface current H, that is the magnetic field intensity, will be equals to surface integral of kds cross air by 4 pi r square. Similarly, the expression 20.8 is showing that H for the volume current, that is equals to the volume integral of j dv cross air by 4 pi r square. So now, where air is the unit vector pointing from the differential element of current to the point of our interest. Okay, so as I said earlier, now we are going to take an example, that is, let us now apply, that means we are going to apply the expression 20.6 to understand the magnetic field intensity. Here you see that, as an example, let us apply equation 20.6 to determine the field, that is the magnetic field, due to a straight current carrying filamentary conductor of finite length AB, as shown here in this diagram. So here we are assuming that the conductor is placed along the z axis, and its lower limit is A and upper limit is B, and we want to find out the magnetic field intensity at this point, which is denoted by the point P. Now the point A is making an angle with the P, say alpha 1, point B is making an angle with the P, and this z axis is alpha 2. So this is the limit. We can also consider the alpha 1 and alpha 2, and we want to find out the magnetic field intensity at this point P. And here we consider that the current flows from point A, where alpha equals to alpha 1, to point B, that is where alpha equals to alpha 2, that you can see that. Now to find out the magnetic field intensity at this point, first we need to consider a small length in this current carrying conductor. So here we have considered a small length, and this length you can consider dl, and the current element present in this dl length is idl. So here, and we can apply the expression 20.4, that is dH equals to idi cross r by 4 pi r cube. And also we have considered this length, for that which the length dl, and whose coordinate is 0 0 z, and for that dl length, dl amount of, that means for this dl length, we are going to find out first the magnetic field intensity dH, here dH. After that, for the total current carrying conductor, we are going to find out the magnetic field intensity at this point P. So for that dl length, we got the expression dH. Now, but we know di is the current element, that is the current flowing through this element. So this is, we can consider dz, because this is the in the z axis, so the length we can consider dz. So di equals to dz az, along the z direction it is moving, so di can be represented as dz az. And r, capital R is r air minus z az, that can be calculated easily from the simple geometry. You see that here this is the vector r, and this length is z, and this length is small r. Now you see that if we want to find out this r, which is starts from this point to this point, then we need to vector addition, we need to get the vector addition of a and b. Here a is moving in this direction and b is moving in this direction. So here the direction of r and direction of b is same, but here direction of a and direction of this z, you can say this is different. So for that we will get r equals to minus a plus b, or r equals to b minus a. I think you understand this one, b minus a, why it is coming. So just like that we will get this expression. That means if we consider this is r, so we need to calculate this a direction, this direction, and this direction, but r the direction of r is in the opposite direction, that is why r is taken negative. So r air minus z az. So here r, capital R equals to r air, sorry, here the r is considered positive in this direction, and a, as you can see that a, actually a is moving in this direction, that is why a, but in this case of the vector addition, the a is negative, that is why z terms is negative. So here r air minus z az. So now if we calculate this di cross r, di cross r means dz az cross r air minus z az. So here the calculation is given in the right hand side, you can see that, and from this calculation we will get r dz fi. And why we are getting this fi, you can understand this one from this. This is the total calculation or the vector addition, that is the cross product is given here. So di cross r is r dz fi. From this calculation you can understand. Now we know that h, we have the dh, so h equals to the line integral. So h equals to line integral of I di cross air. So di cross air equals to r dz fi. So I r dz fi divided by 4 pi. Here you see that 4 pi r cube, so that can be 4 pi and r cube. Here capital R cube, capital R cube. So here capital R means this one is the vector. So if we take the magnitude, then it will be root over of r square plus z square, and as this one is the cube, so that is why we will get small r square plus z square whole to the power 3 by 2. So this expression 20.11 is showing the magnetic field H at the point or the observation point P due to the current element A to B. Now we are going to represent this expression in another form, that is alpha 1 and alpha 2, or alpha in terms of alpha. So here we are taking z equals to r cot alpha. How we are going to get that? This calculation is very simple. You see that, if you see that this one is the z, this one is the r, this one is the capital R. So here you can see that z, if we take this one z by r, then this will be tan alpha. Here this is the angle alpha. So from that we can calculate by using simple geometry z equals to r cot alpha. Now as we got the expression z equals to r cot alpha, then by taking the derivative of this expression, we will get dz equals to minus r cosec square alpha d alpha. And equation, so now if we have this one, then equation 20.11 becomes, you see that h equals to, now limit, as we have seen earlier that the limit is a to b. Now limit is changed from alpha 1 to alpha 2. I r dz equals to, you can see that, minus of r cosec square alpha d alpha divided by 4 pi as it is small r plus z square. So here z square if we take, then small r square cot square alpha. So this r square if you take outside, then square this 3 by 2 and square cancel out, so r cube will be there. So we have r cube. So here, and I is the current, which is the constant current is flowing, so I is taken outside of the integration, minus also taken outside, so minus of I by 4 pi, all these constant terms is taken outside. Integration alpha 1 to alpha 2, here r into r is r square cosec square alpha d alpha divided by, as I said, if we take r square common from that, so r square into 3 by 2. If we take this one here, the 3 by 2 is given, so 2 cancel out, so r cube into 1 plus cot square alpha. So 1 plus cot square alpha, or 1 plus cot square theta means cosec square theta. So here if we put this one, so cosec square theta or cosec square alpha, so square, and here 3 by 2 cancel out, so cosec cube. So here cosec square and here cosec cube cancel out, 1 by cosec alpha, and here r square, here r cube, so 1 by r. So actually we will get 1 by r cosec alpha and d alpha fi. So r is taken outside because the observation point is constant from the z axis. So now we will get minus of I by 4 pi r fi integration of alpha 1 to alpha 2, and we know 1 by cosec alpha means sin alpha, so sin alpha d alpha. Now taking the integration, we will get this minus of cos alpha, limit is alpha 1 to alpha 2. So this is the expression we got of H, the expression of H magnetic field intensity. So minus minus plus I by 4 pi r into cos alpha 2 minus cos alpha 1 into fi. So this is the expression H that we got, I by 4 pi r cos alpha 2 minus cos alpha 1 fi. So the expression 20.13 shows the magnetic field intensity at the point P due to the current carrying straight current carrying filamentary conductor which is placed along the z axis. Now this expression is generally applicable for any straight filamentary conductor of finite length. So the conductor must be straight. The conductor need not lie on the z axis, but it must be straight. So the conductor which we have placed in the z axis, it may happen that the conductor is not placed along the z axis, but the conductor must be straight. If the conductor is straight, then these equations are applicable. Now it can be seen from equation 13 that H is always along the unit vector Fi, along the concentric circular path, it irrespective of the length of the wire or the point of our interest. So that we can understand also, the current carrying conductor is straight, so current is flowing through this direction, so through the z axis. So if we take this expression, in this direction the current is flowing, so the magnetic field must be moving in this direction, and this direction is the Fi direction if we consider the circular path, circular cylindrical coordinate system. So that will be the direction we will get Fi. Now as a special case, when the conductor is semi-finite means that the point A is at 0 0 0 but B is at 0 0 infinite. So here B is at infinite, A is at this point. So if this happens, then alpha 1 will be 90 degree. Here you see that this angle is moving in this direction, so alpha 1 will be 90 degree and B will be, alpha 2 will be 0 degree, because B is moving in the to the infinite, so angle will decrease. So if we put the expression alpha 1 equals to 90 degree and alpha 2 equals to 0 degree, then this expression 20.13 becomes 20.14. So this, by putting this value, we will get H equals to I by 4 pi r into A phi. Now, if we consider the another special case, that means both the A and B are at infinite, at infinity. So, for this case, A is at 0, 0, minus infinity, A is moving downwards, so minus infinity, while the point B is at plus infinity, 0, 0, infinity. So, alpha 1 will be equals to 180 degree because we are moving in the downward direction. So, 90, then 180 degree direction, and alpha 2 as it is 0 degree. So, this expression for this case, second case, this expression becomes H equals to I by 2 pi r A phi. So, for the infinite current carrying conductor, the magnetic field intensity at the point P will be H equals to I by 4 pi r. From this equation 20.15, you can see that the H is dependent on I by 4 pi r. That means I is the constant and 2 pi is also constant. I is the constant current is flowing. So H is only dependent on small r, not the length of the conductor. That is the important information we can get from this expression, that H, magnetic field intensity. If you see that here, magnetic field intensity at this point H is only dependent on the uh, perpendicular distance of uh, the current carrying conductor, perpendicular distance from the current carrying conductor to the observation point, not on the length of the conductor. So that is one important information, that H equals to I by 4 pi r Fi, and H is dependent only on the r. Now here, to find unit vectors Fi in equation 13 to 15 is not always easy. As I said, that we have this, it is obvious that H will be Fi, but by intuition, but according to the calculation, that means whenever we are going to compute this expression Fi, it is not always easy. Okay, but using the intuition, the current is moving in this direction, and right hand thumb rule, the magnetic field will be in the Fi direction, so we can understand. But in terms of the computation, it is not easy. So a simple approach is to determine Fi to determine Fi form is that Fi equals to Al cross Ar. Al is the where Al is the unit vector along the line current, and Ar is the unit vector along the perpendicular line from the line current. That means along the distance smaller, along the direction smaller. So that is all about the today's class, students. uh, we will continue the magnetostatic fields in the next class also. Thank you very much.